Hi friends, welcome back to our YouTube channel. Today we have to discuss about logical equivalence without using truth table in Discrete Mathematics and Graph Theory course with some example problems. The first problem is prove that for any three propositions P, Q, R, P conditional Q and P conditional R is logically equivalent to P conditional Q and R without using truth table. How to prove that? So this symbol is called as logical equivalence symbol. Before that logical equivalence symbol, whatever the formula is there, that can be taken as one compound proposition. After the logical equivalence symbol, what is the formula is there, that can be considered as another compound proposition. We have to prove that this compound proposition is logically equivalent to this compound proposition using logical equivalence formulas. Okay, so that first I am taking LHS part, then we have to prove the RHS part. Next we have to take the RHS part, then we have to show the LHS part. Hence we can say that this compound proposition is logically equivalent to this compound proposition. First I am taking the LHS part. So P conditional Q and P conditional R. Okay. So we already know that some logical equivalence formulas, that is P conditional Q is logically equivalent to negation P R Q. Next one, P conditional R is logically equivalent to negation P R R. Okay, so we have to substitute these two logical equivalence formulas. So P conditional Q is logically equivalent to negation P R Q, and P conditional R is logically equivalent to negation P R R. Okay. Once observing this entire compound proposition, so we have to separate negation PR. So negation PR we have to separate. Then what is the remaining? Here negation PR, here negation PR. We have to separate negation PR. What is the remaining? Q and R. So Q and R. Okay, whether it is correct or not, we have to check again. So this entire thing is multiplied with negation PR. So negation PR is multiplied with Q. We are getting negation PRQ, and negation PR is multiplied with R. We are getting negation PRR. Okay, it is correct. Next one. So this entire thing can be taken as X. Okay, so we already know that negation PRX is logically equivalent to P conditional X. Okay. So negation PRX is logically equivalent to P conditional X. Okay. So in the place of, so negation PR is here. In the place of X, Q and R is there. Okay. So that means P conditional X. What is P value? P value is nothing but P conditional What is X value? X value is Q and R. Okay. So we are getting the RHS part. So this is logically equivalent to RHS part. I am taking LHS part. We are getting the RHS part. Next, I am taking the RHS part. So let us consider RHS part. What is RHS part? P conditional Q and R. Okay, so now we already know that this can be taken as X. So after taken Q and R can be taken as X, simply it is in the form of P conditional X. What is the formula for P conditional X? So that is nothing but negation P or X. Okay, so in the place of P I am writing negation P, or in the place of X what is there? That is Q and R is there. Okay, next step. With the negation PR, we have to multiply the Q and R. So negation PR is multiplied with Q. We are getting negation PR Q, and negation PR is multiplied with R. We are getting negation PR R. Okay, next one. We already know that negation PRQ is logically equivalent to P conditional Q. Next one, negation PRR is logically equivalent to P conditional R. Okay, now we have to substitute P conditional Q in the place of negation PRQ, and we have substitute P conditional R in the place of negation PRR. So P conditional Q and P conditional R. So we are getting the LHS part. Okay, I am taking the LHS part, we are getting the RHS. I am taking the RHS part, we are getting the LHS part. So hence we can say that this compound proposition is logically equivalent to this compound proposition. So P conditional Q and P conditional R is logically equivalent to P conditional Q and R. How can you say that this formula is equivalent to this formula? I am taking the LHS part, we are getting the RHS part. I am taking the RHS part, we are getting the LHS part. Hence, we can say that this compound proposition is logically equivalent to this compound proposition. The second example problem is prove that for any three propositions P, Q, R, P conditional R and Q conditional R logically equivalent to P or Q conditional R without using truth table. So this is the logical equivalence symbol. Before that logical equivalence symbol, whatever the formula is there, that can be considered as first compound proposition. After the logical equivalence symbol, whatever the formula is there, that can be considered as another compound proposition. we have to prove that this compound proposition is logically equivalent to this compound proposition using logical equivalence formulas. For that one, I am taking the LHS part. That one is P conditional R and Q conditional R. Now, so what is the equivalent formula for P conditional R? What is the equivalent formula for P conditional R? Negation P or R. Next, what is the equivalent formula for Q conditional R? It is equivalent to negation Q or R. Now we have to substitute negation P or R in the place of P conditional R. So negation P or R, and we have to substitute negation Q or R in the place of Q conditional R. So that is negation Q or R. By observing this one, in this formula, negate R is there. Here R, capital R is there. Okay, we have to separate R connective capital R from these two formulas. So after separating R connective capital R, then what is we are getting? Negation P and negation Q. Negation P and negation Q. Okay, whether it is correct or not. So negation P is multiplied with R. So negation P R and negation Q R. Okay, next one. Here negation P and negation Q is there. So here negation is there, here negation is there. I am separating negation. After separating negation, so we are getting P or Q. So it is correct or not? So negation is multiplied with P. We are getting negation P. Negation of R is nothing but and negation of Q is nothing but negation Q or R. Okay, this can be taken as X. We already know that negation X or R is logically equivalent to X conditional R. Okay, so in the place of X, what is there here? P or Q. Conditional. In the place of R, only R is there. So P or Q conditional R. So I am taking the LHS part. What we are getting? P or Q conditional R. This is the RHS. It is logically equivalent to RHS. We are taking the LHS. I am getting the RHS. Next, I am taking the RHS. Let us consider RHS. What is RHS formula? P or Q conditional R. Now, so this entire thing can be taken as X. Okay, so now it becomes X conditional R. What is the formula for X conditional R? Is logically equivalent to negation X or R. Okay, so in the place of X, P or Q is there. So here negation X means negation of P or Q. R, capital R. as usual. Okay, next one. Now negation can be applied to whatever the formula is there within the parenthesis. So negation of P is nothing but negation P. Negation of R is nothing but and. Negation of Q is nothing but negation Q. R. Next one. So negation P is multiplied with R. So then we are getting negation P R. This and is same. Negation Q is multiplied with R. We are getting negation Q R. Okay. We already know that negation P R is logically equivalent to P conditional R. Negation Q R is logically equivalent to Q conditional R. Okay, so it becomes in the place of negation P R, we have to substitute P conditional R. And in the place of negation Q R, we have to substitute Q conditional R. It becomes P conditional R and Q conditional R is, that is LHS. So I am taking RHS, we are getting LHS. I am taking LHS, we are getting RHS. So hence we can say that P conditional R and Q conditional R is logically equivalent to P or Q conditional R. Okay, in this way we have to solve the problem. Now we can go for third example. Prove that for any three propositions P, Q, R, negation P and negation Q and R, or Q and R or P and R is logically equivalent to capital R. So right hand side only capital R is there. Left hand side this compound proposition is there. Now we have to take this entire compound proposition on the LHS side. We have to show the RHS side. Okay, that means we are taking LHS part, then we have to show the RHS part. Hence we can say that this formula is logically equivalent to this formula. For that one I am taking the LHS part. LHS part is this one. Okay, now here I am applying two laws. That two laws are, first one is associative law. Associative law. So I am applying associative law for this part. Okay. So how we are applying? Negation P and negation Q and R. I am taking this one. So the parenthesis is for negation Q and R. So it is logically equivalent to negation P and negation Q and R. Okay. So the parenthesis is for negation P and negation Q. Okay. So what we are getting? In the place of negation P and negation Q and R, we are substituting this one. So negation P and negation Q and R according to associative law. Next, here I am applying distributive law. So what is the distributive law here? Distributive law is, so Q and R or P and R is logically equivalent to Q or P and R. So this is the distributive law. So Q is multiplied with and R. We are getting Q and R. This one is R. P is multiplied with and R. We are getting P and R. Okay. Here Q and R or P and R here is there. So it is logically equivalent to this one according to distributive law. So that we have to substitute Q or P and R in the place of this one. So we are getting Q or P and R. So this is according to associative law. This is according to distributive law. Next one. Here I am separating negation from this part only. Okay. After separating negation, we are getting negation of P or Q. So whether it is correct or not, negation of P is nothing but negation P. Negation of R is nothing but and. Negation of Q is nothing but negation Q. According to De Morgan's law. Or Q or P, I am taking P or Q according to commutative law. So here I am applying two laws. First one is De Morgan's law. De Morgan's law. So that is negation of P or Q is logically equivalent to negation P and negation Q. Second law is commutative law. Commutative law. What is commutative law here? Q or P is logically equivalent to P or Q. So I am applying these two laws. Okay. Next one is here by observing this entire compound statement, here and R is there, here and R is there. Okay, we have to separate and R from this entire component. So what is the remaining here? Negation of P or Q or, so P or Q and R. Whether it is correct or not. So negation of P or Q is multiplied with and R. We are getting negation of P or Q and R. Or next P or Q is multiplied with and R. We are getting P or Q and R. Okay. Now, so here this thing can be taken as X. Now it is also taken as X. Okay. So it is in the form of negation X or X. So negation X or X is logically equivalent to true. We already know that negation X or X is logically equivalent to true. So in the place of X, P or Q is there. So negation X or X. That means negation of P or Q or P or Q is nothing but true. Okay. So according to this formula, true and R. True and R. Next, what we are getting true and R? Okay. In the place of R, we are substituting true value. So after substituting true value in the place of R, we are getting true, and true is nothing but true. We are substituting false value in the place of R. So we are getting true and false. We are getting false value. Whatever the truth value we are substituting in the place of R, the same truth value we are getting. So that means, so true and R is logically equivalent to R. Okay, how we are getting? In the place of R, we are substituting true value. True and true is nothing but true. That means whatever the truth value we are substituting, the same truth value we are getting. Next, in the place of R, we are substituting false value. True and false is nothing but false. Whatever the truth value we are substituting here, the same truth value we are getting here. So true and R is nothing but R. So this is RHS. I am taking LHS, we are getting RHS. Hence we can say that, therefore, so negation P and negation Q and R are Q and R, or P and R is logically equivalent to capital R. Okay, we are taking LHS part, we are getting RHS part. Hence, we can say that this formula is logically equivalent to this formula. So, in this way, we have to solve given problem. Next, we can go for another example. Example problem is, prove that for any two propositions P comma Q, P conditional Q conditional P is logically equivalent to negation P conditional Q without using truth table. Okay, for this problem I am taking the LHS part, we are getting some value. I am taking the RHS part, we are getting some value. This value is logically equivalent to this value. Hence, we can say that this formula is logically equivalent to this formula. So, this is the procedure we have to follow to solve this problem. Let us consider I am taking the LHS part, P conditional, Q conditional, P. Okay, we already know that Q conditional P is logically equivalent to negation Q or P. Okay, so we have to substitute negation Q or P in the place of Q conditional P. So we are getting P conditional, so negation Q or P. Next one. So this entire thing can be taken as X. Okay. So it is in the form of P conditional X. So what is the formula for P conditional X? P conditional X is logically equivalent to negation P or X. Okay. In the place of P, we have to write negation P. In the place of conditional, we have to write R. In the place of X, we have to write negation Q or P. Okay. Next, here I have to apply the commutative law. Okay. Commutative law is negation P or negation Q. So here what is the commutative law? Negation Q or P is logically equivalent to P or negation Q. This is the commutative law. Okay. Next, here I am applying the associative law. Okay. The associative law is the parenthesis is for this one. After applying the associative law, the parenthesis is for this one. So it becomes negation P or P or negation Q. So after applying the associative law. Okay, simply we have to change the parenthesis. Okay. Next one. We already know that negation P or P is nothing but true. Negation P or P is logically equivalent to true. Okay, so that we have to substitute true in the place of negation P or P. So true or negation Q. Now, in the place of negation Q, we are substituting true value. True or true is nothing but true. In the place of negation Q, we are substituting false value. True or false is nothing but true value. So whatever the truth value we have to substitute in the place of negation Q, we are getting only true value. So here the formula is true or negation Q is logically equivalent to true. Okay, how we are getting? In the place of negation Q, we are substituting true value. True or true is nothing but true. In the place of negation Q, we are substituting false value. True or false is nothing but true value. Whatever the truth value we are substituted in the place of negation Q, we are getting only true value. Hence, we can say that true or negation Q is nothing but true. After simplifying the LHS part, we are getting true value. Next, I am taking the RHS part. Let us consider RHS part. So that is negation P conditional Q. So we already know that P conditional Q is logically equivalent to negation P or Q. So that in the place of P conditional Q, we have to substitute negation P or Q. Next one. This entire thing can be taken as X. This entire thing can be taken as some P. Or this entire thing can be taken as S. Okay. Now it becomes S conditional X. What is the formula for S conditional X? Is logically equivalent to negation S or X. Okay. So, in the place of S, we have to write negation S. In the place of S, what is there? Negation P is there. For that one, I am applying negation. Or X. In the place of X, what is there? Negation P or Q. Okay. Next one. So, we already know that negation of negation P is logically equivalent to P. Okay. So, in the place of negation P, we have to write P. So, P or negation P or Q. Okay. Here I am applying the associative law. Associative law. In the associative law, the parenthesis is for this one. After applying associative law, the parenthesis is for P or negation P or Q. So we already know that P or negation P is logically equivalent to true. So we have to substitute true in the place of P or negation P. So remaining is Q. So what is the equivalent value? In the place of Q, we are substituting true value. True or true is nothing but true. In the place of Q, we are substituting false value. True or false is nothing but true. So whatever the truth value we are substituting in the place of Q, we are getting only true value. So that we can say that true or Q is logically equivalent to true. Okay, so this I am taking LHS part, we are getting true value. I am taking RHS part, we are getting true value. Hence, we can say that LHS is equal to RHS. What is LHS part? So that is P conditional. So Q conditional P. So is logically equivalent to negation P conditional Q. Okay. In this way, we have to solve logical equivalence problems without using truth table. Simply, we are using logical equivalence formulas. In the previous videos, we are doing one video, logical equivalence formulas. So check that video. That video is helpful for solving these problems. I hope all of you understanding this video. If you have any doubts, please put your doubts in the comment section. I will try to clarify your doubts. If you really understanding this video, please subscribe my YouTube channel. So Divvela Srinivasa. After subscribing my YouTube channel, click on the bell icon to get the future updates in my YouTube channel. Thank you one and all for watching this video. In the next video, we are solving 2 more example problems on logical equivalence without using truth table.